Thank you for joining this lesson. We're going to study angle properties of circles together with chords and tangents. So the question says in number 24 that the figure below shows a circle center O. So this one is the center O passing through points A, B, C, A, B, D, and E, just as you can see. TDC is tangent to the circle at D. Line AB equals to 1.96 centimeters. Line BC equals to 23.04 centimeters. Then the angle BDC equals to 40 as indicated. And another angle EDA equals to 55 degrees still as indicated. The first question, giving reasons, find the size of the angles. Then some angles are listed here. What I would like to advise is that for you to give a reason, you don't actually need to state a lot of things. You need to, after identifying the size of a particular angle, just provide the mathematical approach that you have employed just towards the exact value of that angle, or the mathematical property about angle that you have engaged for you to arrive at the exact size of that particular angle. So as we're going to look at the values of these angles, I would like to remind you of our approach here for purchasing airtime for all networks. So please go to your M-Pesa menu, Lipa na M-Pesa, the paybill number 737356. Then the account number is your own phone number that you're buying airtime for, or it can even be your friend's phone number, a friend that you're buying airtime for. And now you enter the amount, then you proceed with the transaction, and the airtime shall reflect instantly. So please utilize this facility and invite your friends for the same. Let's check at these angles now. We are told that the angle at this point is 40. After seeing an angle of 40, the first thing you should ask yourself, is there another angle which is going to be equivalent to this one? And how do we get equivalent angle? One property that leads us to getting equivalent angle is angles subtended by the same chord at the circumference of the circle are usually equal. But now, this one is an angle made by a tangent and a chord. So we ask ourselves, is this chord subtending another angle at the circumference in the alternate segment? Yes, at this particular point. Therefore, we usually say angle subtended by a chord and a tangent is usually equal to the angle subtended by the same chord in the alternate segment. So the chord BD is the one that produces the angle at A. So it is also equivalent to 40. So the angle is called DAB. So angle DAB is equivalent to 40 degrees. This one is angle in the alternate segment. Angle in the alternate segment. Angle in the alternate segment. It must be equal to the angle made by a chord and a tangent. Again, we can try to fill a few other angles, but it is good you know that the angle that we are interested in is the angle at D, EDT. EDT, the angle at this particular point. There are several ways through which we can find this angle. One is that we can check that AOD is a diameter now that it passes through the center of the circle. And we know that angles subtended by a diameter at the circumference are usually 90 degrees. So we will be very right to conclude that the value of this angle is 90, and also the value of the angle at this point is also 90. Now, those values being known, then we can get the angle at A and also the angle at D. In this way, we take 180 and we subtract 90 and 55. So the remaining angle at this point shall be 35. We also do the same for this particular 90, 40, and the remaining angle here, which becomes 50. Yeah, something like that. So with this now, we can use two approaches to find the remaining angle at D, the required angle here. We can use two approaches. One, we can take 180 and we subtract all the other angles there, because you can see 55, 50, and 40. 55, 50, and 40. Then this will give us 35 degrees angles on a straight line. Angles on a straight line. That is a property that we have applied. Something else that we can use at that particular point is we can say, you see the first principle that we applied for us to get the first angle can also be applied, but now in the reversed approach, in that for the first one, we were given the angle between a chord and a tangent. For us to get the angle in the alternate segment is also 40. In this particular case now, we have the angle in the alternate segment as 35. Now ours is to get the angle made by the chord producing the angle in the alternate segment and the tangent. It also has to be the same. So we can conclude directly that the angle between chord ED and the tangent TDC is the same as the angle chord ED produces in the alternate segment. And the one in the alternate segment is already calculated to be 35. Therefore, the other one is concluded to be also 35. So that is how we work out such a question. Look at the angle we are asked again. BCD. The angle BCD. BCD means the angle, the acute angle at this particular end. This one now can be done using several approaches. In this way, the angle at this point is known. This is 90, the whole of it. We also know the angle here as 40. So using triangle ACD, we can mark this one as now 50 degrees. Or still at this point, we can use 90 at B. When we use 90 there, and we're already having 40 down here, then the remaining angle is still 50, using now triangle BCD. So we can use any triangle. So we can say that the angle here is going to be 180 minus the provided angles, which are 90 and 40. This will give us 50 degrees angles in a triangle. Angles in a triangle, that way. So that is all about the angles that the examiner demanded. We have calculated them. We can look at part B now. Find the length of the radius of the circle. Now the length of the radius of this circle can be found using several approaches. Allow me give it two approaches for now, whereby we will say the length of AB is known. Then the angle, the triangle that is ABD, is right angled at B, which means we can apply trigonometry in this way. The opposite angle to length AB is 50. That is the opposite angle. And also the adjacent is 40. So we can use cos or sine for us to get the hypotenuse now, AD, because both cos and sine relates hypotenuse. In this manner, when I extract the whole triangle ABD, which is right angled, let me bring it here. The triangle is a technical issue, not having the exact diagram, but I'm trying to use some sketchy work to help us. Remember, this is point O, whereby the whole of AD is a diameter. So at B, we have a right angle. This is 1.96. I hope it is 96. Yeah, exactly, 96 centimeters. Now, these angles are 40. This one is 50. So when we use sine or cosine, we will still get the same, because the cosine of 40 is the same as the sine of 50. So they are all the same. It depends on the ratio that you use, because 40 and 50 are complementary. And for complementary angles, the sine of one is usually equivalent to the cosine of the other. So if we work with the cosine of 40, we say the cos of 40 is equivalent to the adjacent length, which is 1.96 out of the hypotenuse, in this case, which is a diameter. Let me call it even small letter d, diameter. So the hypotenuse is diameter in this case. The length AD, which is the hypotenuse, is also the diameter in this particular triangle. So now we can say, when we cross multiply, d by the cosine of 40 should give us 1.96. So d will be equal to 1.96 out of the cosine of 40. At this point now we can get the value. So 1.96 divided by the cos of 40. So this shall be 2.559. So that for us to get the radius, we have now to divide this diameter by 2. This gives us 1.279 centimeters. So this is our radius to an accuracy of 4 significant figures. Remember, I said that the sine and cosine of complementary angles are usually equal. So at this point, even if we had used the sine of 50, it will have a value equivalent to the cosine of 40 that has earlier been used. So over d, and you'll discover that d equals to 1.96 out of the sine of 50. Sine 50 being the same as cosine of 40 will still give us a d, which is equivalent to 2.559. And we proceed to get the same radius of 1.279. Now, alternatively, apart from trigonometry, that is trigonometry 1, the simple trigonometric ratios, we can still apply what we call the cosine rule. The sine rule, that is, sorry. The sine rule, which says that sine rule, which relates sides and angles, can be equivalent to, or is equivalent to, twice the radius of a circle where the triangle has been inscribed. Let me show you how I mean this. So assuming that the triangle we have is ABD inscribed in the circle given, then we will say, applying now sine rule, we will be talking about if we apply, let's say we start with this length because it is having the opposite angle known. So 1.96, when we divide it by the sine of 50, when we divide it by the sine of 50, when we divide it by sine 50, we will get twice the radius of this unknown angle. Twice the radius of this circle. Therefore, 1.96 divided by sine 50 is equivalent to, so 2r, in other words, the value of 2r will be 2.559. So that r itself will be, after dividing by 2, which is 1.279, to 4 significant figures correctly. So you can see we are getting the same answer after using the sine rule as we are getting after using the trigonometric ratios. So that is it. Remember to subscribe to this platform and also to share the link with your friends. Thank you so much.